Good day. This is MEG 224, Engineering Mechanics, Dynamics. Lecture 6, Planar Kinematics of a Rigid Body, an updated version of Part A. This can be found in Chapter 16 of Engineering Mechanics, Dynamics by R.C. Hibella. So the lecture objectives. The objectives of this lecture is to classify the various types of rigid body planar motion, then to investigate the rigid body translation and angular motions about a fixed axis, planar rigid body motion. The planar motion of a body occurs when all the particles of a rigid body move along paths which are equidistant from a fixed plane. There are different types of rigid body planar motion. In order of increasing complexity, they are translation, curvilinear, rotation, and general plane motions. Translation. This type of motion occurs when a line in the body remains parallel to its original orientation throughout the motion. Here, we have a body moving from left to right. And on this body, there are two points. The 2 points move in a straight line. They are moving in straight lines, and those straight lines are parallel to each other. And this is the type of motion that we call rectilinear translation. So when the paths of motion for any 2 points on the body are parallel lines, this motion is called rectilinear translation motion, as found in figure A. Then, if the paths of motion are along curved lines, which are equidistant, and that type of motion is called curvilinear translation, as shown here. The points describe curved paths, and they are always equidistant from each other. Rotation about a fixed axis. When a rigid body rotates about a fixed axis, all the particles of the body, except those which lie on the axis of rotation, move along circular paths, as shown in figure C. Here, we have particles in this body, and then when the body rotates about a fixed axis, the particles, they rotate about this fixed axis. The particles that will not rotate are the ones that lie on this axis of rotation, general plane motion. So when a body is subjected to general plane motion, it undergoes a combination of translation and rotation, as shown in figure D. So there, the paths of those points are neither parallel or curved. So the translation occurs within a reference plane, and the rotation occurs about an axis perpendicular to the reference plane. So this is the axis of rotation, and the XY plane is this axis of rotation is perpendicular to the XY plane. Examples of bodies undergoing these motions are shown in the figure below. So here we have a piston that is going, or that is having a rectilinear translation motion. It's going in the positive and the negative X directions. Here we have wall, because it is a circle, it's circular. So we have wall that restricts the movement in the X direction. This point here is undertaking a rectilinear translation motion. Then at this point, this disc is rotating, while this arm too is rotating about the axis, about the fixed axis. So, but this connecting rod at this point is rotating, and at this other end, it is going X direction. So it's observing what we call general plane motion. The connecting rod here is rotating while it's rotating at this point and this point. So the connecting rod here will come down and go around. So it's observing what we call curvilinear translation. While the disc here and this connecting rod here, they are observing rotation about fixed axis. So consider a rigid body which is subjected to either rectilinear or curvilinear translation in the XY plane, as shown in the figure. This is the body. So is observing either rectilinear or curvilinear translation. So the position. So locations of points A and B on the body are defined by with respect to the fixed axis X and Y. This is fixed axis. So, and then we're using position vector RA for point A and RB for point B. The translation or the translating X prime, Y prime coordinate system is fixed on the body and has its origin at A. So this is the translating axis that's translating with the body. But this axis here, XY axis, is a fixed coordinate system. So it does not move. But this other one is moving with this body. So this point A is hereafter referred to as the base point. This point A. So the position of B with respect to A, is denoted by relative position vector, which we call, this is the relative position vector, which we call R of B with respect to A. By vector addition, RB will be RA plus R of B with respect to A. So RB will be RA plus R of B with respect to A. Velocity. A relationship between the instantaneous velocities of A and B is obtained by taking the time derivative of this equation, which yields VB is equal to VA dr of B with respect to A dt. We know that R, it says that RB is equal to RA plus RB of A with respect to, so we just put D dt, D dt, D dt. So the RB dt will give you VB, and then the RA dt will give you VA. Then we now left this other one for further evaluation. So here VA and VB denotes the absolute velocities, since these vectors are measured with respect to X and Y axis. And then the term, the R of B with respect to A dt is equal to 0, since the magnitude of R of B with respect to A is constant by definition of rigid body. Since the body is rigid, then R of B of A does not change. So, and because the body is translating in the direction of RB of A is also constant. Because the body is translating, the direction of RB of A is also constant. Therefore, we have this guy is 0, then we now have VB is equal to VA. So acceleration, taking time derivative of this, that is the VB dt is equal to the VA dt. So this yields a similar relationship between the instantaneous acceleration of A and B. So A of AB, acceleration of B, or acceleration of point B is equal to acceleration of point A. So the above two equations, this acceleration and the velocity equations, indicates that all points in a rigid body subjected to either rectilinear or curvilinear translation move with the same velocity and acceleration. Now, let us look at rotation about a fixed axis. So when a body rotates about a fixed axis, any point P located in the body travels along circular paths. So angular motion. Since a point is without dimension, so a point cannot have angular motion. Only lines or bodies that undergo angular motion. For example, consider the body shown in figure A and the angular motion of a radial line R located within the shaded plane. So this is the body that we're talking about, and then this is the line that is located within the shaded plane. This is the shaded plane, and this is point P, making a circular movement or circular motion around point O, and its direction is always towards point O, else it will go in a straight line or go away. So angular position at the instant shown, this instance shown, the angular position of R is defined by angle theta measured from a reference line R. So from reference line to R. So this is the reference line, this is angle theta, and this is R. So angular displacement, the change in angular position, which can be measured as a differential d theta, is called the angular displacement. So this is the reference line, this is point P, which makes an angle theta with R. Then the point P or line R moves a small increment, which is the theta, and that the theta is called the angular displacement. This vector has a magnitude of the theta measured in degrees or radians or revolution, where one revolution is 2 pi radian. Since motion is about a fixed axis, this motion here is about this fixed axis O, the direction of the theta is always towards or along this axis, so it's round. Specifically, the direction is determined by the right-hand rule. That is, the fingers of the right hand are called with the sense of the rotation. So these are the fingers. This is the sense of rotation of the theta. This is the sense of rotation of alpha, which is angular acceleration, and then omega, angular velocity. So that in this case, the thumb or the theta points upward. So in 2 dimensions, as shown by the top view of the shaded plane, figure B, both theta and d theta are counterclockwise. And then the thumb points outward of the page. Theta, the theta, theta, the theta, they are anticlockwise. Angular velocity. The time rate of change in angular velocity is called, the time rate of change in angular position is called the angular velocity, which is omega. Since the theta occurs during an instant of time dt, then omega is the theta dt. This vector has a magnitude which is often measured in radians per second. It is expressed here in scalar form, which since its direction is along the axis of rotation. So, as shown in figure A, when indicating the angular motion in the shaded plane, we can refer to sense of rotation, whether as clockwise or counterclockwise. But the thing is, we have to be consistent. Once you start your solutions or your workings with clockwise direction as being positive, you must maintain that clockwise position as being positive throughout that work. If you say counterclockwise is positive, then you must maintain that throughout. Here we have arbitrarily chosen counterclockwise rotation as positive and indicated this by the curve shown in the parentheses here. So realize, however, that the directional sense of omega is actually outwards from the page. It comes out. So angular acceleration. The angular acceleration alpha measures the time rate of change of the angular velocity. The magnitude of this vector is alpha is the omega dt, that is change in angular velocity per unit change in time. It's also possible to express alpha, which is angular acceleration, as alpha is equal to d2 theta, the t2, that is the second derivative of displacement. Now, the line of action of alpha is the same as that of omega. However, its sense of direction depends on whether whether omega is increasing or decreasing. If omega is decreasing, then alpha is called angular deceleration and therefore has sense of direction which is opposite to omega. By eliminating the t from the equations above, we obtain the differential relations between the angular acceleration, angular velocity, and angular displacement. Namely, so here we say that we can eliminate the t from the earlier equations. The earlier equations, we have alpha is equal to the omega dt. So dt will now be the omega over alpha. Then we have omega is the theta dt. Then we can now say the t is equal to the theta over omega. So we have the t here to be the omega over alpha, and then we have the t here to be the theta over omega. So we can equate the two. Then we have, which will now be equal to the omega over alpha. So that will now give us that alpha, the theta, will be equal to omega, the omega. So, and that is how this equation was gotten. That's how they came about this equation. And the similarity between the differential relations for angular motion and those developed for rectilinear motion of a particle, v is equal to ds dt, a is equal to dv dt, and a ds is v dv, should be apparent, which we have already proven or shown in earlier classes. So constant angular acceleration. When the angular acceleration of the body is constant, a is equal to ac, then the earlier equations can be integrated, and then when it is integrated, or when they are integrated, they yield a set of formulas which relate the body's angular velocity, angular position, as well as time together. So these equations are similar to equations used for rectilinear motion, that is the Newton's 3 equations of motion. The results are this. So omega is omega naught plus alpha t, which is similar to V is equal to U plus AT. Theta is theta naught plus omega naught t plus half alpha c t squared. That one is equal to S is equal to S naught, that is S is S2 is equal to S1, which is initial position, plus UT plus half AT squared. Then omega squared is omega naught squared plus 2 alpha c into theta minus theta naught, which is similar to V squared is equal to U squared plus 2AS. So here, the acceleration, the angular acceleration is constant. Hence, theta naught and omega naught are the initial values of the body angular position and angular velocity, respectively. So motion of point P. As the rigid body in figure C rotates, this figure C, as it rotates, point P travels along a circular path of radius r with center at point O. So this path is contained within the shaded plane shown in figure D. So this is the top view of this plane. So this is the point P, this is the direction of the velocity, and then this is r from O to P. Position and displacement. The position of P is defined by the position vector r, which extends from O to P. If the body rotates through an angle d theta, then P will be displaced, and then ds will be r d theta. So velocity. The velocity of point P has a magnitude which can be found by dividing ds and r d theta by dt, so that we have that V is omega theta. Oh, sorry, omega r. Here, is ds dt, d theta, dt. Since dt is on both sides, so it's still the same thing. So ds dt gives us velocity, while d theta dt gives us omega. As shown in the figures C and D, the direction of V is tangential to the circular path. So it's tangential. So both the magnitude and direction of V can also be accounted for by using the cross product of omega and Rp. Here, Rp is directed from any point to the axis of rotation. Rp is directed from any point on the axis of rotation to point P, as shown in figure C. We have V, the velocity, is equal to omega cross Rp. In order, the order of the vectors in this formulation is important, since the cross product is not commutative, because omega cross Rp is not equal to Rp cross omega. So notice in figure C how the correct direction of V is established by the right-hand rule. So it is omega that crosses Rp. The fingers of the right hand are called from omega towards Rp, that is omega cross Rp. The thumb indicates the correct direction of V, which is tangent to the path in the direction of motion. The magnitude of V is V equals to omega rp sine phi, which is the result of what we call product, the cross product of two vectors. Cross product, that is A cross B, is equal to AB sine phi. So V is equal to omega cross R. Acceleration. The acceleration of P can be expressed in terms of its normal and the tangential components. The point P that is moving in a circular motion, its acceleration has two components, the normal component and the tangential component. And the normal component, AT, is the V dt, and the tangential component is AT dV dt, while the normal component is V squared over rho. So rho is the radius of curvature, which is equal to R, and the V is equal to omega R, and the A is the omega dt. Then we have that AT is alpha R. We know that the V dt AT is equal to the V dt, which is equal to d omega R over dt. So, which is the omega dt R, which is R alpha or alpha R. So that is how this guy here was gotten. So then we now say that here normal acceleration is V squared over rho. So V squared AN is equal to V squared over rho, and V is omega R, which is omega squared R squared over R. So this R will cancel out. So we now have omega squared R. So the tangential component of acceleration, figure E and D, sorry, figure E and F, represents the time rate of change in the velocity's magnitude. If the speed of P is increasing, then tangential acceleration acts in the same direction as velocity. But if the speed is decreasing, tangential acceleration will act in the opposite direction, that is deceleration. And finally, if the speed is constant, acceleration, the tangential acceleration is zero. So these are the two